Okay, so now let us look at what we call the type 2 improper integral. So the definition of this type 2 improper integral is defined as follows. So the integrand, or the integral function, becomes infinite at a point within the interval of the integration. Okay. So basically we can put this into three different categories. First one is if we have a function fx, it is continuous at this interval left open a to b close, and is discontinuous at x equals a. Okay. Then this integral from a to b fx dx, and as we mentioned, because it's not continuous at x equals a, and also you can see that if we plug fx with a, it goes to infinity. For example, it's something like this. Okay, so you see this a, you can think about it, it's a vertical asymptote for this, and you know, if you're trying to calculate the area between end of the curve from a to b, so you construct this integral in this way. So the basic idea, what you do here is replace this a with another variable c, and then you evaluate this definite integral first, and then you take a limit, let c approaches a from the right, because we are approaching a from the right hand side. Okay, so this actually is a one-sided integral. And similarly, the other situation is you know, if the function is continuous from a is closed, left closed, right open, and is discontinuous at x equals b, and then the integral from a to b fx dx going to become into integral from a to c fx dx. This time you let c approaches b from the left, excuse me. So look at this graph, right? So if we want to figure out this definite integral, that means if, let's see if fx is positive, if I want to figure out the area and the curve between a and b. And apparently at x equals b, you know, it's a vertical asymptote, meaning your fx goes to positive infinity. So the strategy is you take c, you know, is between a and b, right? You evaluate it, and then you can calculate that, and then let your evaluation is going to be some expression involved with c. Take that limit, let c approaches b from the left. So this is again one-sided limit. So that's the second situation. And then the third case is you see the function is discontinuous at x equals c, but it's continuous, you know, at the interval from a to c, union from c to b. And we can see from a graph it's something like this. Okay, so if you want to figure out this integration from a to b fx dx, you need to split your integral into two parts, from a to c, and then plus from c to b. Okay, about how to handle this one and this one, well, it will go back to 1 and 2 categories. Okay, so this is what we call the type 2 improper integral. And now let us look at one example here. So suppose we have one example. Let's see. Suppose this is a graph. Fx equals 1 over square root of x. Okay, and then let me label this part as 1. Now apparently this is going to be the origin. So the question is, okay, find the area under the curve, fx equals 1 over square root of x from 0 to 1. Okay, and So if we remember the area under the curve, and of course this y over square root of x, it is positive number, so we can easily see that this is going to be integral from 0 to 1, y over square root of x dx. But look at what we have here, and notice that at x equals 0, my function is discontinuous, okay? And also it goes to positive infinity. So under this situation, what we can do is, we'll do it as, let's say, integral from c to 1, 1 over square root of x, okay? And then this is a definite integral, and then I take the limit, let c approaches 0 from the right. Okay, so basically the idea is, if I that this is c here, and I can easily to calculate the area under the curve here, and then I let that representation, let c approaches 0 from the right, okay, to see if that limit exists. And if it exists, then we call this integral converge, and if not, just diverge, okay? So let's calculate this definite integral first. So integral from c to 1, 1 over square root of x dx, that is c to 1, x to the power negative half dx. And then, so if the antiderivative of this one is x half, actually over half, right, evaluated from c to 1, which is 2 square root of x, evaluate between c and 1. So you plug in, you're going to have 2 square root of 1 minus 2 square root of c, which is 2 minus 2 square root of c. Okay, so that's this piece. Now we're starting to evaluate the limit of this expression, which limit c approaches 0 from the right, 2 minus 2 square root of c. And apparently this one side limit for this part is 0, so this whole expression is 2. So bingo, we actually got it. The area under the curve from 0 to 1 actually is 2. Pretty surprising result, right? Because it looks like as x approaches 0, this kind of goes to positive infinity, then the area might keep growing, but turns out, no, very surprisingly, the area is a fixed number. So we finished this problem. Okay, so hope you enjoy this video, and happy watching.